Hello again. We've been talking a lot in class about how to determine what a customer's problem is, and the point of that is we want to actually solve the right problem. It doesn't do us any good to build a beautiful piece of software that the customer doesn't want. Now, let's assume that we're able to figure out what the problem is and come up with a good solution to it. So we know we've come up with we know what the product should look like, how it's going to work, we've got a good design. Now we need to get around to actually building the product. Okay, so let's talk a bit about our development process. So with software development, our big goal at this stage, this construction phase, we've got to build the software. So we want software that does not have defects, doesn't have bugs in it. We want a really high quality piece of software that does what we expect it to do. All right, it works correctly as we believe the correct software should be working. So how do we go about doing this? Well, it turns out that the biggest issue that we really face to this problem is integration. We're working in a team environment. So our problem is really that how do we get a bunch of developers or engineers to work together such that they're able to build this cohesive piece of software? And this integration problem, if we don't do it right, we often will just end up with software that doesn't work. And that's the biggest defect of all. It's nothing. The other issue is when we integrate things, often the developers, we've got other sorts of communication problems and all sorts of things, and that introduces bugs, defects as well. So integration ends up being sort of the biggest hurdle to overcome for shared software development. We've got to be able to integrate all of our work into a cohesive whole that's free of defects. Okay, and that really then is sort of the second biggest issue, is that as we work, unfortunately, we often introduce new bugs into. It's not just unfortunately, we might be putting code in that we think is good and it might have bugs, but not only that, but it often turns up bugs in the old code. And again, this is an integration problem. Oh, now when I interact with your code, with my code, things don't work right anymore. Or I had to change something to get my code to work, and I caused bugs to exist and to appear in the software. And so we really need a shared development process that helps us avoid this problem. All right. So that's what we're going to talk about now, is a shared development process. And the biggest thing that we need to make a shared development process work is a shared repository. Okay, so here we are, we're going to do a shared development process, which means team's working together on this. And absolutely, this is required, is that we have to have a shared repository often abbreviated and said a repo for the team's code and related files. You're also going to use your repository to store documentation. You can use it to store drawings for the project. You do all sorts of things, but you're often, anything having to do with the project will go into a shared repository, okay? And all of this stuff is under source control. Via a version control system. For example, Git, and we're going to use Git in this class. There are other existing version control systems, but Git has really come to dominate a lot of the industry now, especially open source projects. Now, shared repository, what that means is we're going to have a repository that we all agree is the main source of the code. It's the place where the final product sits, the final code sits. And so we choose a location for that. And for us, we're going to use GitHub. There are other ways to have a shared repository, but GitHub works really well with Git. And so that's what we're going to do. And we're going to follow processes that work and match with GitHub. So if we've got let's talk a bit about version control systems. Now, you've used Git and GitHub in the previous course, but we really haven't used them very much for version control. We largely used them as a way to turn in homework and to deploy things to Heroku. But the real question, you're probably always wondering, why am I deploying it? Who's the customer? You know, so what we've got some of the pieces, but now we need to understand more about what really these systems are used for. So a version control system is a wonderful thing that holds a history of file changes. So all the files and all their changes, and this allows us to be able to go back to old versions. And this is really important because we might change some code, think we've done a good job, but now we see all sorts of problems and bugs, and we want to figure out what's the difference between what we did now and what we had before. Well, thank goodness we've got the old version. We can easily do comparisons, and if we just decide that we've made a horrible mistake, we can even go back to an older version and use that. We can roll back. All right. This is really important. We don't want to lose our work at all, and we don't want to lose the history of our work. Now, it's important to understand, though, that version control systems work a little bit different than a lot of the systems that you're used to nowadays. Nowadays, a lot of the systems you use, like Google Docs, are automatically saving things for you in the web. And if you shut down your browser, you don't lose any work. That's not at all the way version control systems work. Only the user selected versions, so you have to tell it what to save and when to save it. So only user selected versions are saved via commits. That are pushed to the shared repository. Now, we'll get into some of the details in a later lecture about Git. Your commits will save the versions of your code in a local repository. But again, we want to think about it in terms of the shared repository, and to get them, then we've got to push them there. Now, so that's wonderful. We can save all these different versions of our files. What else? Well, the other really nice thing is that it allows for concurrent, at the same time, editing of the same source code file. So you can have the exact same file, but it allows you to do this via this process known as merging. And this is definitely something that's not like Google Docs. And so what I mean by that is that, so we're going to be able to as two developers can be working on, let's say it's the same they're working on the same view in Ruby, okay? It's the exact same, it's like new.html.erb, okay? They've both got that file open and they both can be editing that file, but they each are editing their own copy of that file. It's not like Google Docs where Google is letting you see what one person is typing while you're typing. No, you get to work as a developer in your own world with your own copy of the files, but you're both allowed to edit the same file at the same time. And what it does is it's going to, at a later point, when you commit and push those things, we're going to end up eventually merging them together, okay? Now, so via this merging, it could produce, we might, because we are editing the same file, conflicting changes will require human intervention to resolve. So the system is smart enough to say, you know what? You both were editing in the same place of the file. I actually don't know. Should I take your changes or your changes? You both were working at the same time. Who is right? And that requires human intervention to resolve. It's great that the system can do that. Now, the system also tends to be pretty smart and says, oh, you were editing up here at the top of the file and you were editing at the bottom of the file. I don't have a problem with that. That's fine with me. So it's only usually when you are editing in the same place of the file that the system will say, I have a conflict. I don't know what to do. I need you to tell me what to do, how to choose what the final version is. But this is great. Without this sort of system, we would have chaos as we attempted to work on the product. So we would either share a set of code and all be trying to share editing of it, which doesn't really work at all. Because imagine you're just in a Java program and someone's in the middle of a line and you'd like to compile it. You're going to get syntax errors until it's fixed. There's no way you could coordinate. You need your own set of files. But you still want to be able to edit any file in the system. Okay? Much older version control systems had a notion of you had to check something out and then you owned it. And no one else was allowed to edit it until you checked it back in. The new systems allow concurrent editing, and it's very impressive. All right, now these systems can, just so you know, they can store binary files. The biggest one that you would want would be images. So you're going to build a web app. It's really nice occasionally to have some images in it. But these systems cannot, they don't know how to merge them, okay? Or even show differences, okay? These systems are designed for source code. They're designed for plain text files that they can figure out how to merge. They can show you differences between them. You can store the binary files, and you're going to need to store them in your version control system if you're going to build a website and have some images. But you need to know that it's not like one person can edit an image and another person edit the image and then, oh, let's resolve the conflicts. That's not the way it works. It's going to be one image or the other image. Okay. So we've got our shared repository. That's great. We know our shared repository is going to all be with a version control system. We're going to use Git, and our shared repository is going to live at GitHub. Now, we need some rules as part of our shared development process that lead us then to actually get to this ability to be able to do the integrations, not have the bugs. Okay, so rules for using this type of system is, first rule for developers always is that the repository is always kept in a shippable state. And what do I mean by shippable? Shippable means could go to the customer. All right, it's ready. You could package that thing up and you could send it to the customer, no problems. You could deploy it to a website and the customer goes, that's great. That I can, yep, that's a quality piece of software without bugs in it. So it's always kept in a shippable state. Well, what does that really mean? Because we're going to be working on it. Isn't there going to be some in-between state where it's not shippable? And the reality is what we do is we've got this great ability that we can, so what does it mean to be shippable? Was that we can deploy our main branch. This is particular to web apps and what we're doing in the class to Heroku, and get a working web app. So that's what it means. This means it's always going to be in shippable state, which means we can always deploy our main branch to Heroku, and we've got a good working application. This is that the customer would say, you're right, that works. Now, this also means that, so we'll talk about how it is that we're able to get work done and keep the main branch good in a moment. But it also means that, again, this main branch is approved, so to speak, for the customer to use. So we could always send it to the customer. Okay. But then this is important. This means that this main branch is not something with experimental code, something to try out. Or, hey, I wanted to put something in there so that another developer could check it out. Absolutely not. The mentality is whatever is in that main branch in our shared repository is something that we want the customer to see. It wouldn't be any problem at all to go hit the button, deploy to Heroku, set up the system and say it's there, it's running, it's good, we're happy with it. It's not like, oh yeah, Bob's half-tested feature is sitting there, lurking there. Absolutely not. We're never going to let the main branch be in anything other than a shippable state. So we always got to keep that in mind. And that's a very important rule, and we're going to work to obey that. And we'll show you the techniques that we're going to need and to allow us to support that. Now, there's another important rule. So that's the first rule about dealing with the shared repository. But the second one, so all the developers know that no one is allowed to, quote, break the build. Which basically means to introduce a flaw. We don't want any flaws, but in particular, ones that break the build are flaws that prevents other developers from working or cause deployment. So we're trying to get it out there to the customer on Heroku or whatever, deployment or existing tests for that matter. Anything that breaks existing tests to fail. So you might introduce some small bug. You don't want to do it, but that's okay. Other people can keep working and we can come back and we can actually fix that bug. But if you do something to that repository, that main branch of the repository, that then when other developers need to use it, they can't actually even do their job anymore. You've broken their ability to keep working. That's called breaking the build, okay? Or if someone on the team says, oh, I want to deploy it to the customer and it can't be deployed, or it's deployed and then you click a couple things and you get like method not found and it's like obviously broken, that's breaking the build. We don't do that. Now, so let's give you an example of how, in the traditional sense, what it means to break a build. So a huge amount of software in this world is compiled. Take, for example, Java. You always have to, you write the code and you have to say build, and then you're actually able to run it. It has to compile first, and you'll end up with these syntax errors, okay? So let's say you have a syntax error in Java code that's committed to the main branch. Well, that when everyone else gets a copy of that and they try to use it, no one can compile. So no one can compile the project. And that is really bad, okay? That is a broken build. We can have broken builds in the web sense as well. So I'm trying to work, but because of something you checked in, my stuff doesn't work anymore. Imagine you screwed up the routes file in Ruby on Rails. Well, the moment they try to do anything and there's a syntax error in the routes file, 1,000 errors strew up the screen. And they're just like, who broke this? Okay? We don't do that. We don't break the build. We don't prevent other work from getting done. All right, so with those two rules, we need some mechanism. So those are our goals. But we need some processes in place that help us achieve those goals, because they're fine and they're lofty. Oh yeah, I am always going to be sure that it's in a shippable state. Yes, I am. And oh yeah, you know it, I won't break that build. Well, we really need something that's we'd love to be able to trust all of our developers to do that at all times. But we also need to verify that we are maintaining that behavior that leads to it's always shippable and we haven't broken the build. Okay, and what's the solution? The solution has been known for a long time. In the simplest sense, it's a daily build. Okay, in the more advanced form, it's a continuous integration, where continuous integration largely means doing lots of builds every day rather than just one build. And again, the purpose of this is going to be to enforce the rules. Now, I've mentioned that there's this good book, and I've assigned some reading from it, The Dynamics of Software Development. So in the Dynamics book, rule number 32 is, if you build it, it will ship. A play on Field of Dreams with Kevin Costner. If you build it, he will come. So if you build it, it will ship. This is a rule dating from 1995. Yes, from the ancient days. But it wasn't something that was always known in software. Was this idea that, oh yeah, we're going to build the product every day. Instead, people used to work for long periods of time and then try, oh yeah, let's bring all our code together now and let's see if it works. And it didn't. And it was a disaster. So yeah, at Microsoft, basically Dynamics, they introduced this concept of a daily build. All right. And so what we need to do is we need the same thing. So we need, at a minimum, this is our way of testing to see, are we keeping to those rules that we're going to keep in a shippable state and not break the build? At a minimum, product must be built and what we call smoke tested. Smoke testing is the idea of it is to check basic functionality. When you guys deploy or bring up your web apps, largely you're smoke testing. You're like, I'm going to click some links. I'm going to create a user. I'm going to see if I can delete this, add this. Hey, it looks like it's working. Great. That's smoke testing. There's lots of ways people have described where this terminology comes from. I like to think of it coming from building electronics, and then you plug it in, and if it starts to smoke, it's failed the smoke test. Okay. But anyway, and smoke test at least once each day, or at least once a day. Oh, I'll say each day. That's good. Once each day. Okay. Now, sometimes in MSci 342, students, for whatever reason, don't actually do anything to change the repository on a day. And they're like, do I still need to build it? The answer is no. If you haven't changed it, there's no need to build it. Now, it's often the case that there probably should be work coming in at a steady pace. But basically, after anything has changed in the main branch of the repository, and again, we'll be talking about all these branches later, but anything that's changed in the main branch, yes, you need to go through, you need to do a build, you need to deploy, you need to smoke test. All right, that's basically the idea. And if multiple changes come in a day, you need to do your deployment at least once in the day. All right. The idea of continuous integration basically is everything that, if there is a change to main, it kicks off a new build and a new deployment and a whole suite of tests to make sure everything is still working. Now, all right, so you're like, that's cool. Okay, we're going to do these builds, but how does that really enforce the notion that we're not going to break it, that we're going to keep things in shippable state? Well, if the build is broken, so you do this and you find, yep, someone broke the build. All right. All the engineers, all the developers must stop work. No one keeps coding away. A broken build is a disaster. And that's how serious this is that we ask everyone to stop work, and the team works to fix. All resources go to fixing the problem. Oh, we've discovered the build's broken. Everyone stop. We're not going to spend our time casting blame. We know someone made a mistake. Try not to be yelling and mean to them and all sorts of things. But we as a team, we're going to get together now and we're going to fix this doggone thing. Okay? And if you want to, you could think of this like, it's like an assembly line. And something bad has happened. And if we keep going, it's just going to turn into a disaster down the assembly line. So it's like hitting this emergency stop button. No, wait a minute. Stop the work. Because you're either going to be wasting your time building on top of junk, or you're just going to be sitting, you're just not going to be contributing. This is to really, we don't let this happen. We're going to fix this integration problem immediately. All work stops. All right. Now, historically, back in those days of Microsoft where they had this notion of the daily build and so forth, originally my understanding is that they, so sort of historically, and I don't know of anywhere that does this anymore, because it's sort of a shaming, and it's not a nice thing to do. So I don't recommend it for teams at all. But historically, it was the last person to break the build who had to do the build, a test deployment of it, and smoke test it. So, you broke the build the last time. It's your job now. Every day, the first thing when you show up at work, you kick off the build process, you watch it, you make sure it works, you deploy it, you run some tests, and then you report to the team, is our build good or not? And then when the next person who wasn't actually careful enough breaks the build, it's their job. And so people would talk about, we'd have stuffed animals or a mascot or something and it would pass from person to person. This is not really done anymore. Now, you at the next stage in a larger team, you might very well have a build engineer who's responsible for this. But the build engineer really is most likely working to maintain the system for continuous integration, which is a whole bunch of software to automatically, on a regular basis, run builds, report things back to people, what's the status of all the automated testing, all sorts of things, maintaining a website with all this. And so it's a whole large job. It's an extremely important part of being able to succeed at the shared software development process. We've got to keep the software working as we build it. We can't go backwards. We can't lower the quality of our product. We can't have it cease to completely work, okay? So it's a very important thing. It's been learned that it's really critical. We're going to get that shared repository. We're going to be sure that our main branch is always good enough to go to the customer, and we're never going to break the build. All right, so now the next question is this. All right, that's all wonderful and good. Now, what are some of the things that I need to do to be sure that I don't screw it up? All right, so you want to know how to add functionality to it. So adding functionality to the product. So you want to write some code. And we want to obey our rules. We're going to go with a multiple step process and I'm going to explain this at a high level. And then later we're going to dig into more of the way that Git works and how we interact with GitHub, down to the level of individual commands eventually. All right, so developers, we can think about that we work using, I'll put it in quotes because it's sort of true, sort of not true, copies of the shared repository, okay? And all work is done on branches other than the main branch. Now, what is a branch? You can think about a branch largely as another copy of the repository. So it's basically like we're all going to get a copy of the shared repository, and then from there, we're going to make another copy of it, and we're going to work on this other copy that's not the main version. So it's just sort of like our own copy of a copy. And then we're going to be able to send those changes back to the shared repository. Those changes then end up getting put back into the main branch on the shared repository. And then when everyone else wants to update from the main repository, they're able to get our changes. All good. That's the high level. So let's talk a little bit more about this then. So again, we're going to work on these branches. These are our own copies. So this way, also when we all have our own copies, we're not stepping on each other's feet. Okay, we're able to have our own environment, and if everything's working great for me, it's working great for me and I'm getting a lot of work done. If someone else is introducing bugs and they're having problems, that's their own problem, okay? Now, at least once a day, the developers pull changes from the shared repository and merge them into their working branches. So because I have a copy of the repository and other people are busy doing work and they might be updating the shared repository, my copy is going to get out of date. So if I keep working based upon the out of date notion of the code and the product, when I go to try to put my code back, people are going to say, but we changed that last week. We changed that yesterday. Like, your code doesn't integrate. Your code doesn't work with our code anymore. Go back, fix it. So to save yourself that hassle that you have coded something that doesn't work with other people's code, you need to make sure that you keep updating from the main shared repository so that you stay in sync, so that your changes are synced up and can actually integrate with other people's changes. Great. So we've got our own copy. We're going to work on a copy of the copy. We're going to be sure to keep it up to date with the other changes that people make. Now, as we work, one of the big things that we're going to do is make sure that our code is high quality. So developers, make sure via testing their code works before asking for it to be added to the main branch. This is a developer's responsibility. In the past, we might very well have had notions of having people in quality assurance and having testers. That concept still exists in some teams, but a lot of teams are moving to a notion that the engineers, the developers themselves, are responsible for the quality of their code, and they're responsible in fact of being able to show to other people that it works. Okay, so when you believe you have it ready, this asking for it is called a pull request. So basically, when ready, you'll push the code, the dev, so when ready, let's actually add in, commits and pushes. You're going to push your branch to the shared repository. This is, again, it's going to be sitting here at GitHub. And then submits a pull request often abbreviated PR. And the pull request is asking to merge their branch with the main branch. So saying, I am ready for my software to be put into that version that a customer would see, software that would be considered in a shippable state. And all right, and what we do is we put in a formal request, and this is part of our development process. Okay, pull requests are not part of Git. They are part of the process of GitHub, and we are adopting that process, and they're part of then our development process. So we put in a request to our team that our work is now ready, and it's sitting up there in the shared repository, not in the main branch, but in our branch. There's a copy of it now in the shared repository, and we would please, if possible, could we please merge it with the main branch? All right. Now, there's an important thing. We'll talk some more details about PRs, but a really big part of a pull request includes, so of the software that the code you have written, so it includes automated tests. So any automated tests that you've written You know, and we could say and or, because you might not have any manual tests, or documented manual tests. And a manual test literally is something that says, it's a written down, it says, to test this, go here, type this, you should get a response like this. That's one test. All right, here's another one. Do this, and you should get this as the result, and so forth and so on. And if you have these manual tests, you have to have written them down. You have to have documented them. There has to be a file then that you're part of all of these files that you're saying, yes, it's these things, all right, that I want you to consider. So the idea here is really sort of providing proof or evidence of working code, of quality working code. So it's your job as the developer, not just as you're building stuff to make sure it's good, but it's in your request to your team that you're like, I hereby present the evidence about why my code is considered to be high quality. We should have high, it's probably not going to be proof, but we're going to have a high certainty that I probably haven't screwed it up. And I am going to supply it to me. And the way to think about this is, imagine you were working for a manager on something. Your manager gives you a task and you come back and you say, I'm done. And the manager says to you, prove to me that you're done. Well, usually it's not a problem. You're going to show what you did. Or maybe your manager asked you to write some code and the manager's going to say, prove to me that your code actually works. What would you do to prove to your manager that it actually works? You're not going to be like, well, isn't quality assurance going to test it for me? No, they're not going to test it for you. It's your job. I mean, think about all of the engineers in the world. It's their responsibility to make sure that the work that they do is high quality. So software engineers have that same responsibility. It's not, we don't rely upon other people to show that our work is good. We have a responsibility to use methods, and one of the biggest methods to achieving high quality is actually to be having a rigorous set of tests to be able to increase our confidence that we haven't screwed up. It's rarely a proof that things are right. All right, so great. We submit that request. It's waiting. Now we need someone on the team to evaluate our work. Okay, so our process now includes that one or more members reviews the code, and we'll call it the diff. The notion is they are going to look not only at the code that you submitted, but they're going to actually view the differences between what you've done and what was there before. Oh, you changed this, and oh, you changed that. And so GitHub, and Git in itself, but GitHub provides very nice means for people to go, show me all the differences between what used to be in the code and what they've changed and what they've added to it, so that I can see the differences. And so they look at the diff. And this is important, runs the tests to verify the quality of the code. And by the way, if your pull request is filled with a documented set of manual tests, it means the code reviewers go through and do the manual tests. It would be tedious compared to automated testing, but you know what? You got to have something. You can't just simply say, is it okay? Will you accept it? At a minimum, they would have to read your code and try to determine whether it's right. But they shouldn't have to just read. They should have the assistance to say, oh yeah, so I agree with your logic and your reasoning and your process that because you developed it against these tests, that then if these tests work, that things are good. So it's a whole, they need to see not just your code, but also your reasoning as to why, as you developed it, that you believe that you were building the right thing that was of high quality. So now, often you're going to have, as a result of this, a back and forth that happens before code is approved. So before the code and whatever the tests are, because your tests matter too, where the code and tests are approved. And you can't, we're not going to have, our process in this course and a lot of organizations is you're not allowed to get your code out there to the customer until we've given it a rigorous review, tested, and understood whether it's any good. And we're not going to let that happen either. You know, in addition to the tests you supply, usually you will also have tests done to avoid regressions. So if there's existing automated tests in the product, those will also be run to make sure that you haven't caused them to start to fail now. All right, so then we're finally to the point that if they approve of your code, so once approved, code is merged into the main branch and is now part of the product. And so you can see that this whole entire process is really working hard to make sure that, yes, if we follow this and we work well as a team, we should be actually making sure that together we are going to maintain those rules, that the repository stays in a shippable state, and certainly the build's not going to get broken then, because we've really worked hard to make sure that what gets put into there works, and that should not cause the build to break then. All right.